Okay, so we're finished with the logarithms for now. And so the next topic is Euclidean spaces. Or more precisely, just say Euclidean plane, the Euclidean plane. Okay, so we have seen the plane, the xy plane already. Okay, so what is the difference? The difference is crucial based on the where we are from what direction we're arriving at this xy plane, and this is the way we did it early on. We started with functions. Okay, and then we looked at, well, functions, they were either given by formulas, they were given by tables, and so on. Okay, and from that, what we did is we, in order to illustrate it, we would plot its graph. We plot its graph, and we, as an illustration, we plotted its graph on the xy plane. Okay, so then what that entailed was the axes. Just to refresh your memory, the two axes, x and y, they kind of appear in a different way, because we're talking about y equal f of x. So the relation between x and y is function f. There is nothing else. So such as x is time, y is location. Okay, so could be. Then, and this is the point I would like to make here, is it's possible that, or likely, that there is nothing similar in the, or related in the units that you will use for x and y axes. Okay, so otherwise they're two identical lines. But then what else is similar? We mark the origin. So on the x-axis there's an origin. On the y-axis there is an origin. Then we indicate the directions on the x and y-axis. They exist like this to begin with, and then we place them together like that. But because x might be, like I said, time, and y might be location, there is no relation between the units that we use for x and y, and therefore, if we look carefully at what we have produced, we are having not what frequently we do have is a square grid. The grid does not have to be square, it is rectangular. Okay, like this. So, well, just to show you that how typical it is, this is Excel, and it is the one that handles data in a number, well, the standard for handling data. And the data is on the left. It's some kind of function. On the right, there is a chart which illustrates the data, those two columns that are highlighted. The one is for x, the other one for y. And then this is what you can do with Excel. That illustration is truly just an illustration of the data and nothing else. So I can resize it like that, and it will be still valid. It's the same illustration, or illustration is different, but the data is the same. This is entirely up to me to use nothing but a mouse, and the data is the same. So it's entirely our own convenience. Once again, if you look at the grid visible behind the graph, it is rectangle. I could try hard and make them look similar. So the x's are just two well, Excel really doesn't even want me to make a grid, a square grid. It keeps it rectangular for whatever reason. So that is not the point of what we have been doing with the xy plane. There is nothing specific about the relation between x and y, and the measuring horizontal and vertical directions are unrelated to each other. Okay, so it's the same function, same x and y. Say it could be represent motion, for example, an object thrown in the air, as its height depends on time. And how do you do it this way? Stretch it, shrinking, it's the same It's the same function. So anyway, that's the way we have been doing it. Now we are taking a different angle, and that different angle goes back to Euclid, in which is we are studying literally plane geometry. Plane geometry. So you have a piece of paper, as they did, and then on that piece of paper they had lines, they had triangles, they had circles. Okay. Imagine that. Well, how about squares? How about squares? So if I take that picture on the right and try to stretch it, the square will not be a square, it will be a rectangle. A circle will not be a circle, it will be an ellipse. Okay, so that makes it impossible or unacceptable for us to adopt this kind of approach to the xy plane. It is slightly different because now we have x and y. Or what has happened, we just take that piece of paper and start measuring things on the xy plane, okay? Not in some abstract sense. X and y are some quantities, some numbers, and we just plot them as a matter of convenience or illustration. It is the opposite direction. We're starting with some geometry on the plane, and then we're trying to understand how we can add algebra to this. So geometry on a piece of paper. Now we want to do algebra with that geometry, and the answer is we still need what we call it xy plane, but the better term you might remember is what's the other term for the xy plane as I plotted here? The Cartesian plane, yeah. So naturally Descartes was, what is it, like 1600 or so, and Euclid was a few thousand years earlier, so that certainly they didn't know that. The Cartesian plane then is, it applies to both of them, whether x and y are related or not, it's the same idea. But as you can see, yes, now the assumption is for this part of the course, the assumption is that the units are the same, which allows us to deal without ambiguity with things such as circles. Then we can tell circle from an ellipse. We are not allowed to stretch the graph, the xy plane anymore. It is what it is. And the main thing is that you will discover is that the angles. I'm not sure if this one is quite clear. Let me maybe pick another picture. The angles also stretching and shrinking changes angles, right? So the angle seems here looks like, I don't know, 30 degrees. But if I go on and shrink it like this, what's the angle? Now it's maybe 60 degrees. So that kind of a representation of data does not rely on angles data because we don't care. But if we're doing actual geometry, the shapes matter as well as angles. So we can do triangles, we can actually do slopes in a more precise way. So anyway, what happens is we take this picture. The idea of what we are about to do is to take the xy plane, well, the Cartesian plane that we already know, and do what? And superimpose it, which I'm going to try now, on our piece of paper. Okay, so it is certainly not something that you haven't seen, but let's just to make that point, this is what we're doing. Okay, so that grid is now put on top of those little pictures. So for the point of doing measuring without measuring. So the picture on the left is pre-measured. So all the units have been measured. The angles are assumed to be 90 degrees. So everything is ahead of time, is already known, and we just have to match those geometric figures on the right with those with the grid. How? Through coordinates. So that part we also know. Every point on our Cartesian plane has a representation by a point, and that by two coordinates. And so, which means that with some care, we can do the same with our geometric figures. We already have done certainly a little bit in that direction, and that is the lines. Nothing much else. Nothing much else. But so lines are straight lines are y equal mx plus b plus x equal say C. Okay, so for the vertical lines, that's the inconvenience of the representation of the circles of the lines by this standard form. So this is the standard standard slope-intercept form, and its drawback for geometry is that we cannot apply to vertical lines. Vertical lines cannot be represented in this form. So that's why we had a better representation. So slope-intercept form. We had another one, which includes both all lines, including vertical lines. It is this: ax plus by is equal to c. This one is the advantage is that it doesn't matter if the line is vertical; it still falls into this category, so it can be studied as such. Okay, so. Okay, so I'm not going to talk again about the representation of points by coordinates, but let's just put the point here, and this is the point P, and we find the representation for it with 2, 3 are the 2 coordinates. So that part doesn't change. What does change is 2 things. The way I explained it is that the units on the x is the same on the y, but also there now will be measurements. We want to measure distances along not only along x and y axes, but also diagonally. Okay, so that requires distances, discussion of distances, starting on the axes. Okay, so that's the number one topic that has not been discussed as far as the Cartesian plane is concerned, is how to measure, and I put measure in quotation marks, distances. Because we don't want to measure anymore. Everything is pre-measured, so instead of measuring, we want to compute them. Compute them in terms of their coordinates. Compute distances between points in terms of their coordinates. Okay, it helps if you start with dimension 1. In my opinion, it is so much easier if you start with the simplest case. You have 2 cases here, and which of the number of dimensions that you're handling, and the simplest is 1. So dimension 2 is the plane, but then we never stop. We're going to go to dimension 3, dimension 4, and so on. So it's better to start with the simplest case, and the simplest case is dimension 1. So the idea still applies. We have our straight line. By the way, we have, before I do that, Microsoft Paint has an option for the grid. So if I have my pictures, whatever I want to study here, okay, but then I can put it on the grid if I just do this. Oops. Okay, the grid is there, and so in case you don't know, you see it on the right, bottom right is tiny numbers over there. Bottom left, you see? So as I move my mouse around the picture, the coordinates of the point are visible here. Okay, so just a warning is they're in the wrong direction. So the horizontal direction is left, right, but the vertical is down. So as you can see, when I'm over here, it is 4, 2, meaning that the x-coordinate is 4. This and the vertical direction is 2, because the y-x is pointing down according to Microsoft. Okay. But otherwise, it's very convenient, so you can actually do it one point at a time. If I need to find a point with coordinates, say 600, 700, I just move 600 until I reach x-axis, which is 600, and then I move vertical until I reach 700. Okay, so here somewhere. Okay, like this. So it is the coordinate system is built into Microsoft Paint. Okay. Okay. So, but as far as the theory is concerned, in actual mathematics, we start with dimension 1, and to remind you, we have the direction, we have the origin, and we have the units. So that is the Cartesian line, if you prefer, x-axis, Cartesian line, or coordinate line, if you prefer. I think it's better. I don't think Descartes thought about lines. He was concerned with the plane, but the idea is the same. So we have a line, a geometric object, and we add some way to measure it as if it is like, imagine a road, and you put milestones on it, and that way you don't have to actually do any actual measuring or even observation. All you have to look at outside the window and look at the milestone you're passing, you know where you are. Okay, and that way, what does it give you? It also gives you that ability, if these are indeed milestones, it will give you the ability to find out what the distance is, the distance that you have covered. So first of all, every point corresponds to a number, its coordinate. So for example, this point over here is, say, P as a point, as a dot on the line, but it's also 4, it's its coordinate. Okay? So with that understanding, what is the distance? What is the distance between P is equal to 4 and, say, Q is equal to 6? What is the distance? What's the distance?
That would be 2.
The answer is 2. Okay. So, so the idea is we need to come up with a formula. So what is the formula? General formula for the distance between 2 points. So P and Q, what's the distance? So how did we get 2? From 6 and 2, it is 6 minus 2. 6 minus 4, right? So that's how we got 4, how we got 2. 6 minus 4 is 2. That's the distance. But it is measuring the distance from 4 to 6 is the same as measuring the distance from 6 to 4. Okay? So what's the formula, if you know? What's the formula of the distance between P and Q? Q minus P. But what if Q is equal to 4 and P is equal to 6? It is the absolute value. So the correction is the absolute value of P minus Q, which is the same as the absolute value of Q minus P minus Q. Okay, so it's the same thing. Say G P Q. Distance from P to Q is the same as distance from Q to P is defined to be simply the absolute value of the difference of the two numbers. Okay, so as long as you stay on the x-axis or you stay on the y-axis, you know how to compute difference. You just subtract and you take the absolute value. Okay, so it is when we move on to dimension 2, it becomes slightly more complicated, because this is where we are now. Say this point is 1, 2, and this point is 5, 4. Okay, so this is P, this is Q, and we need to know the distance. So once again, the question is, what is the distance between P and Q in terms of their coordinates? Well, that part is only helps if we actually understand what we're trying to accomplish here. And in other words, if we just invoke Euclid and Euclidean geometry before dealing with the Cartesian system, how do we find distance between 2 points if everything is pre-measured? So it is a diagonal distance. It's like you have a, well, maybe you have some kind of a rectangular object, and you want to, well, maybe a tile, okay, and you want to measure or compute. You cannot measure. If you take, you can measure, obviously, but if you only know the size of the tile, but you size dimensions of the tile, you don't know the diagonal, which is what you want to find. No, that's you. I think you're thinking area. So a rectangle with known dimensions, such as a tile. How do you find the diagonal without measuring? So once again, it has nothing to do with the coordinate system right now, but once again, a very practical question is an object, maybe it's so large that you cannot measure, or maybe your measuring tape is just too short. But you know the dimensions. One is 3, the other one is 4. What's the diagonal? It is. It is. Yeah, it is called the Pythagorean Theorem. Indeed, once you see a triangle here, then that becomes clear, right? This is my triangle. It happens to be a right triangle. Why? Because it is a rectangle, which means that the base angle on the right is in fact a right triangle. So then this is a right triangle, and then to find the diagonal that I describe as a diagonal is in fact the hypotenuse, right? So it is equal to 3 squared. D squared is equal to 3 squared plus 4 squared. So 9 plus 16 is equal to 25. And you can actually say that D is equal to 5. Okay. Naturally, if the numbers are not as round as 3 and 4, the computation still works. The idea still works. We just, it doesn't matter. We really want to take the Pythagorean theorem and apply it to our situation. Why it applies? Because the axes are perpendicular to each other by design. Why they were designed this way? Because we wanted to apply the Pythagorean theorem again and again and again. So because our measurements in a horizontal direction and in the vertical direction have been carried out ahead of time. Okay, so this is, in fact, this in the previous discussion, this is, let me move it around a little bit. This is what I'm talking about. This is the horizontal dimension of our rectangle. What is it? It is the distance between the coordinates of P and Q on the x-axis. Right? So specifically, this is 1 and this is 5. Okay, so that way we know the horizontal dimension of my rectangle, which happens to be 5 minus 1 is equal to 4. And then we do the same with the vertical direction, vertical dimension of my rectangle. So once again, it will lie between the two coordinates, the 2 and 4. And so the vertical dimension of my rectangle will be 4 minus 2 is equal to 2. Okay, so then we have our triangle is what is it? 4 by 2. Like this, 4 and 2. Okay, and so the Pythagorean theorem applies. And so if this is D, then D is equal to, D squared is equal to 2 squared plus 4 squared and so it works out not as well as last time. It is 20, and d is equal to square root of 20, which would be the answer then. Okay, so that is all just pretty much solves the problem. We just need to write the formula, which will look similar to this one, just slightly more complicated because there will be 4 numbers involved. So let me try to have a setup for this problem so that we can solve it in a more general way. So one point P, which has coordinate x1, y1. Over here there is a Q with coordinates x2, y2. And these are the 4 numbers that are we're only allowed to use. So this is dpq, the distance between them. So we already know that we're gonna put together the x's and subtract, and put together the y's and subtract. Okay. So in this manner, so let's just write it out. The horizontal dimension is, and this time I don't have specific numbers, so I'm not going to be subtracting literally, but I will be using this formula over here for measuring things horizontally or vertically. So the horizontal dimension is what? That's right, x2 minus x1. So a horizontal dimension, which means that all y's are ignored, and we just subtract x's, not forgetting the absolute value. The vertical is the opposite. The vertical dimension is y2 minus y1, absolute value. Okay, so and then so these 2 are known. So the first one is the other one, this one, and the vertical is that one. The Pythagorean theorem applies. So Pythagorean theorem tells us that dpq is squared is equal to the sum of the squares of these. So x2 minus x1 squared plus y2 minus y1 squared. Which almost does it. Certainly it is a formula that is just as good as it is, without doing anything further, because it actually reminds you that this is nothing but the Pythagorean theorem. So the Pythagorean theorem, if you want to remember where the formula comes from, that's the way to do it. As you can see, the square of the one dimension plus the square of the other dimension gives you the distance, the hypotenuse squared. Okay, so but the formula traditionally is solved for PQ, so that creates a square root, a big one. And then these 2 expressions, we usually drop the absolute values. Why do we drop the absolute values? Right, it doesn't matter. It's called the distance formula. So any 2 points then on the xy plane, if the coordinates are known, then the distance between them is found by substituting numbers into this formula, which is fairly straightforward. The more complex problems that we're gonna face is, and more interesting is such a thing as a circle. So we're gonna use it to study circles. What does it have to do with circles, the formula? Well, actually, a better question is, what is a circle? So, what is a circle? of radius R centered at point P. So it is a plane geometry question. So you certainly know what it looks like, but how do you describe it mathematically? A circle of radius R centered at point P. What makes it a circle? Well, what makes it center? A center at P. Why is it called a center? Not just equal, but equal to R. That's right. So that is the definition. All points are units away from P. Okay, it's well, how you can draw a circle is like this. So this is the center, and you just rotate it. Okay, so this distance remains the same. Your other finger is on the center, and then you have your circle. Okay, and that is the units away from P. In other words, the distance is R. So that is the description, the original geometric description of the circle. You pick a point, you pick R, and then what do? You go in all possible directions, measure R units, and plot a point there. You take all of those points together and you have a circle. Okay, so you can study circles the Euclidean way. So this is the definition. You do all kinds of things, intersections and the, circumscribing circle, inscribed circle, and so on. All of that good, but our interest is how to deal with it in the environment of the Cartesian system. And the life is much easier because we can describe it with a single formula, and the formula is right there. So we choose P is identified as P is x1, y1. At this time, what we're going to do is we're going to say that Q is xy. Xy, which means that it's going to be it's going to be variable. To emphasize x1, y1, to emphasize that those are two fixed. The center of the circle is fixed, but these are this is variable. So we'll allow that extra point. The point on the center is not a part of the circle, by the way. It is just determines the circle, but does not lie on the circle. The circle is the curve. Okay, so so we allow Q to run across or along the circle like this. Okay, so we say, well, suppose Q has coordinate xy. Express xy in terms of what? In terms of those two parameters. And those parameters are simply radius r and the coordinate of P. So the two parameters of the circle are the radius and the center. In the Cartesian situation, it turns into three numbers: r, a number, and two numbers for the coordinates of P. Fortunately, all work has been done. In fact, I'm not going to take the distance formula, but rather the previous one, the Pythagorean formula, in order to write it what it looks like. This is what it looks like. So I take that formula, and I don't do anything really. I just replace x2y2 with xy. So r squared is equal to x minus x1 squared plus y minus y1 squared. Okay, so what this is the equation of the circle. What does it mean? It's not a graph. It's not a graph because all graphs are graphs of functions. So it is a graph, but not of a function. It's a graph of a relation. Okay, so I'll get to that in a moment, but let's once again look at the geometry and make it clear what we're trying to say here. So equation of a circle, what does it mean? It means that every point Q with coordinate x, y that lies on the circle also satisfies the equation. There is a matching statement here. A matching statement. So every point on the circle satisfies this equation, and vice versa. What does vice versa mean? Can you make the converse statement here? Every point that lies on the circle satisfies the equation. What's the converse?
Every point that does not lie on the circle does not.
Every point. That's what I had in mind. Every point that does not lie in the circle. Yeah, it is true, but it's not technically not the converse. It is the converse, but the converse is easier just to change the order of statement. So without doing negation, which is a bit confusing. So what I'm saying, converse is every point that satisfies the equation also lies on the circle. Okay, conversely, every point Q that satisfies the equation lies in the circle. So that is precisely what we want to have. We don't want some description that captures some of the points but not others, and then or maybe finding points that are not there. So it's exactly it. All points on the circle are given this way, as well as conversely every point given by this equation gives a circle. So let me make a little picture here. So to emphasize this, so point P x1, y1 here somewhere, and then we take the radius and like this. Well, you can go in 4 directions like this and measure the radius in the 4 directions to begin with, and that gives you the rough idea where the circle lies, like this. Okay. So specific problems you are likely to encounter would be find the one way or the other. Either the equation is given, you need to describe the circle in some other way, or you have a description of a circle, you have to find a formula. So for example, what is the circle, the equation of the circle centered at 1, 2, radius 2. Roughly what my picture is supposed to indicate. Just plug it in. The values, these are 3 numbers are plugged into my formula. These are the parameters are x1, y1 are the parameters of the equation. The rest are the x and y are the variables. Okay, so once again, so these are the parameters. Those 3 parameters, and the variables are what's left. These are the variables. So they are to be preserved. It's going to be an equation with respect to x and y. So just plug it in. 2 squared is equal to x minus 1 squared plus y minus 2 squared. Conversely, might be more complex algebraically, and such as identify or describe the circle, such as say 1 is equal to x squared plus 2x plus y squared. Hold on a second. Let me put 4 here. Okay, so it is not given in the standard form. That's the standard form in the formula over there in green. Okay, so then to identify what the circle is, you have to turn it into the standard form, and some parts are already there for you for convenience. You can see them. So the number on the left, y squared, is present. What the problem is here, because we don't have x minus something at the top squared. We have x plus 2x. Okay, so what do we do? So I'm supposed to have here x minus something or plus something squared plus y squared. In other words, we are trying to complete a square. Okay? So how do I complete a square, the beginning of which is x squared plus 2x? X squared plus 2x plus one more term. What's the missing term? What? No. I'm talking about complete squares, such as, remember the formula of the square? Well, the answer is, by the way, is 1. So it is x plus 1 squared. That's what completing a square means. Right? So frequently finding that missing term, the one that you have x squared, we have x multiplied by something, and the third term is missing, which is supposed to be a constant term independent of x, and here x squared plus, that is 1. It is that formula, x plus 1 squared is equal to x squared plus 2x plus 1. Okay? So in other words, the missing term is 1. So it will be x plus 1 squared, and I have to make up the difference, so it will be minus 1. Okay. So the answer is then x plus 1 squared plus y squared, and on the right I have 5. Okay? So let's quickly describe what this is. So what's the answer? The answer is you're supposed to describe or identify the circle. We have an equation which has the right form, okay, that green one. So you match it up. R squared is equal to x minus x1 squared plus y minus y1 squared. Okay, so you have to match up the two lines and specify the 3 unknowns. The 3 parameters. The 3 parameters are x1 and y1. What are they? What is R? Match it up. Almost. R squared is 5. Square root of 5. Okay. Then we match up it over here. What's x1? Minus 1. Okay, and finally over here we match y with, we match these. So what's y1? 0. Okay, so that tells you everything you need to know. You know the location of the center, and you know the location, and you know the radius. So you can actually plot it if necessary in a fairly easy fashion. So the point of the center is -1, 0. So it's here. That's the center. It was P. Okay, and then you're supposed to go square root of 5 in all directions. So square root of 5, so it's 2 plus something, right? So here somewhere, and there's some maybe. 1, 2 over here. Okay, 2, and then so I went square root of 5 to the right. I went square root of 5 to the left, and then I do the same up and same down, and that gives me the outline of my circle. So what remains is just to connect it by a reasonable curve. If you do it by hand, that's what you end up with. Okay. So that matching procedure is what once you do the algebra correctly, you can find the parameters by simple examination. Okay. Another type of problem. So these are the two types of problem, 1 and 2, the direct and the converse. And then, but the first one can also have variations, such instead of telling you the radius, you might have to find the radius indirectly. So, for example, what if it is centered at 1, 2, but over here, but the question is, what if the radius is unknown? So this is the center, P, and then the second piece of information is it touches the y-axis. The circle touches the y-axis. You're supposed to determine the radius from this. What's the radius? No. Y-axis, not x-axis. 2, right. So the radius is 2. This is how it touches, like this. Okay, so just indirectly you have to figure out what the missing information is. Okay, so I'll see them all.